So again, what happens is that we have atoms of some gas, and because the atoms collide with each other, their energy of motion is transferred to the internal energy of the atoms, and we have electrons that are actually that are occupying high energy states. Okay? And then one of those electrons can drop to the lower energy state, and in the process emit the photon. In this case here, it happens that the energy difference between the initial and the final state is such that we have here the photon of green light. So that's the light that one collects with a telescope. We typically use the slit to collimate the beam of light, pass it through the prism so that we see which wavelengths are present there. And then what we see is basically one particular line of given wavelength, and that wavelength is basically determined by the energy difference between these two levels. So this is the emission process. The opposite process is illustrated here, and you can do that not just with a starlight, but with any light. You have a light source that emits the light of all possible wavelengths, from blue or violet to red. You collect it with a telescope, again pass it through the slit to collimate it, and now when you pass it through the prism, because different wavelengths propagate through a denser medium at different speeds, different wavelengths will be resolved as separate components. You see the entire spectrum, all the colors present in the source of light. But now if this light is passing through a gas, and the photons that have just the right energy so that they can be absorbed by the electrons, and they can be absorbed if the energy is such that an electron can promote it from one energy level to any other one, right? But the energy must be fixed by the energy difference between the final and the initial state. Those photons will be taken out. They will be missing, okay? So now when you collect the light, and you again collimate it and pass it through the prism, now that green line is missing because it's been absorbed, right? So this is so-called absorption line. Okay, so what the astronomers do is something like this, as illustrated here. See, what happens is that the interior of the star is much hotter than its surface, because the energy is produced in the interior by fusion of hydrogen into helium that requires tremendous temperatures. It won't start unless the temperature is 10 million degrees. And that light then is passing through the cooler atmosphere. In the case of our sun, the surface temperature of the sun is 6,000 degrees. So what happens as that radiation passes through the cooler atmosphere, and because it's cooler, you have a lot of lower energy states of the atoms occupied by the electrons. So they can get promoted to high energy levels through the absorption of photons. So then you might have, then if, depending on which chemical element you have, then for instance, a light that can be absorbed by electron absorbing the photon energy and going from orbital 1 into orbital 2, right? Then that corresponds to a red light, so that particular photon will be missing, and you will get an absorption line in the red part of the spectrum. Then, for instance, photons of green light have just the right energy to to make the transition from level 2 to level 3, and then you would get another absorption line. And then there are also photons that are very energetic that can actually cause the electron to jump from the lowest energy level 1 into this one 3, and then you will get an absorption line at the shorter wavelengths, right? An astronomer on Earth, he collects the spectrum of the star and actually can see which absorption lines are present. And the absorption lines actually are fingerprints of chemical elements. Let me just show you that by one example. Of course, here is the emission spectrum of different chemical elements, but nevertheless, these wavelengths again depend on the energy levels of that are characteristic for an atom. So here are the spectral lines of hydrogen. Here are the spectral lines of neon, the spectral lines of calcium, spectral lines of strontium. And you see that all these spectral lines are different. So the spectral lines, either emission or absorption, actually serve as fingerprints of chemical elements in the atmosphere of the star. When I was an undergraduate student, we had in third year a lab in atomic physics in spectroscopy. Now, I'm like 10% of all men partly colorblind. I can't, sometimes I mix up red and green. Just can't see the difference between certain, I can see the traffic lights, but I mean, there are certain shades of those. So I just couldn't, you know, you stare at the spectrum coming from, we used to get as a source a hot gas of particular element that we had to identify what it is. And I was useless. I had to rely on my partner to recognize the colors, and then I helped with the calculation, okay? But that's exactly what astronomers do. They do this, the analysis of the spectrum, absorption spectrum of the star, and that's how they find out what its composition is, okay? So, as I mentioned before, the result of such observations is that star composition by mass, not by the number of atoms, is 74%, about 3/4, is hydrogen, the simplest chemical element that exists in nature. Its nucleus is just one proton, and it has one electron moving around the nucleus. Then 24% is helium, and 2% all other elements. Now, when people look at the spectrum of stars, they found that there are spectral lines of an element that they did not see on Earth. And that was the spectrum of helium. That's why that element, remember, nucleus here is one proton. In the case of helium, the nucleus consists of 2 protons and 2 neutrons. And then that's why it's named helium, because in Greek, Helios is the name for the sun. So they said, we have this element that has not been detected on Earth, and it was named helium, thought that to exist only in the sun. But then eventually it was found here on Earth. Basically, it's generated deep inside the Earth through the radioactive decay of heavy nuclei, such as uranium and thorium. When they decay, they emit so-called alpha particles, which are nothing else but the nuclei of helium, right? And usually it is detected deep in mine shafts and so on and so forth. So eventually they realize, yes, it exists also on Earth, but it's much more abundant in the sun, okay? So we now know what the composition of Sun's atmosphere is, and that gives us also a good clue as to what the overall composition, chemical composition of the Sun and other stars is.